The topic that I will be covering up today is linear regression model and OLS estimation. Before we dive into this topic, we need to understand the concept of econometrics. So econometric refers to the quantitative measurement of an economic phenomena. It may be a social science in which the tools of economic theory, mathematics, and statistical inference are applied to the analysis of economic phenomena. Let's understand this with the help of an example. Let's take the law of demand, which states that as the price falls, the quantity demanded of the commodity, say X, increases, right? So how can we depict this inverse relationship between price and quantity? That is possible with the help of inverse law of demand equation, which is written as P of X is equal to A minus B of QX. So econometrics has helped us to formulate this equation, and econometrics will help us to estimate these two parameters A and B, right? And one of the most important use of econometrics is that it helps us to empirically testify our economic theories. What does this mean? So I am saying that there is an inverse relationship between price and quantity demanded. But how will I prove that? I'll prove that by collecting all the data which is available to me about different prices, as well as their respective quantity demanded at those prices, and then I will be using that data in this equation. So therefore, we can basically provide an evidence of our theory, right? So that is why econometrics is important, to empirically testify our economic theories. Next, we have the concept of simple linear regression analysis. What do we understand by regression analysis? So regression analysis is basically concerned with the study of how an independent variable is impacting a dependent variable, right? So it is concerned with study of dependence of one variable, the dependent variable, on one or more variables, the explanatory variable or independent variable. For instance, again, in the law of demand, we have price. As it falls, the quantity demanded increases. Now, what is happening here is that when the price has reduced, then the quantity has increased. So basically, the increase in quantity demanded is dependent on fall in the price, right? So in this case, our price is the independent variable, and the variable dependent on it is the dependent variable. And if we represent this more generally in econometrics, we write this as regression of y on x, where y is our dependent variable, x is our independent variable. So in what does this sentence means? This means that we are trying to understand how the x is impacting our variable y. This dependent variable are also known as regressand, or they are also known as explained variables. And x is also, independent variable is also known as explanatory variable or regressors, right? Moving on to the next concept, we have the population regression line. So to understand this, we will be taking up a hypothetical example in which the population consists of 60 families. X represents the weekly income and Y variable represents the weekly consumption expenditure of these 60 families. We are also assuming that this X variable will take on only 10 fixed values, which will be taken from an interval of 80 to 260 rupees. So let's say that X takes on the value of 80, then it takes on the value 100, then 120, and so on and so forth. That means that all these 60 families will have a weekly income of 80 or 100 or 120 and so on and so forth, and nothing below that or nothing above that, right? So as we can see in this table, So X is taken as 80, 100, 120, 140, 160 and so on and so forth. Then on the basis of their weekly income, we have computed the weekly consumption expenditure of every household. For instance, in this case, let's pick up a 70 in the first column. So what does this mean? So let's say that out of these 60 families, there is a family A1 who is earning a weekly income of 80 rupees. We go and we ask them, what is your weekly consumption expenditure? And they tell us that their weekly consumption expenditure is 70 rupees. And that is what this Y depicts. Again, if we are picking up this 90 here, we again, let's say we again have another family, A2, which is earning a weekly income of 120. And on the basis of their weekly income, their weekly consumption expenditure is 90 rupees, right? So that is how we have calculated the values in these columns in this table, right? Then we have taken a total of every column. This is basically summation of Y, right? We have calculated their mean. Mean is nothing but summation of Y with respect to number of observations available in every column here. Now, we have got this mean. But another thing that we need to focus on here is that we are talking about conditional mean of Y, which is equal to expected value of Y given X. Now, why is that? So, when we are talking about mean refers to an average, right? Average value. And average value is always equal to expected value. Fine. Now, this expected value in this case is actually conditional expected value of Y given X. That is expected value of Y given X. Why is that case? Because in this case, the average of Y, the mean of Y is dependent on our X. The average of our weekly consumption expenditure depends on the weekly income of the families, right? So in this case, the weekly consumption expenditure, the average of weekly consumption expenditure is 65, given that the weekly income of families was 80. The average weekly consumption expenditure of households was 101, given that weekly income of households was 140. So that is why we have conditional mean of Y in this case. Now we also need to understand unconditional mean of Y. So when we are talking about unconditional mean of Y, we are actually talking about expected value of Y. This means that we are taking average of all the 60 households in the population, and we are not considering their weekly income. And on calculating this unconditional mean, our value would be equal to rupees 121.20 rupees, right? So that is the difference. In this case, we have neglected the weekly income of all the families. And in this case, we are taking out the average of the weekly consumption expenditure on the basis of weekly income that the households have, right? So that is the difference between conditional and unconditional mean of Y. Then, so now let's come to the population regression line, which is also known as population regression curve. So it is simply the locus of conditional means of the dependent variable for the fixed value of explanatory variable. Let's understand this definition with the help of a figure. So in this figure, I have taken Y as this Y axis represents my weekly consumption expenditure and X axis represents my weekly income. Fine. So I have plotted this. So when I have 80, now in this case, when my X1 is equal to, let's say, 80, my Y is taking on actually multiple values, right? One of the values is 55 at X1 equal to 80. One of it is 60, then another is 65. So we have plotted all those values corresponding to it. Right? Similarly, let's take another case. Let's take the column 160. Right? So we are moving on. And again, under 160, we have multiple values of y. So we are actually plotting all of those values like this. Then again, we have, let's say, x3 is equal to, let's say 200, right? And we plot the corresponding y values. Now, if we look at their conditional mean, we know that this conditional mean is somewhere between these values because it is an average. So let's plot that. For example, here we had 65 and in this case we had 113 and it was somewhere here. And in this case, we had it somewhere 125, which was somewhere here. And let's join all these points. So in joining all these points, this line is known as population regression line. So population regression line is the locus of the conditional means of the dependent variable for the fixed values of the explanatory variables. I hope this is clear. And also one thing that we need to notice is that as we are moving, as x is increasing, our conditional mean is also increasing. And this can be easily actually concluded from the table that as our x value is increasing, the conditional mean of y is increasing, right? Now, next we have the population regression function. So under population regression function, we will actually talk about two types of population regression function. One of them is the deterministic population regression function. So now we have seen that expected value of y depends on the value of x. So can we write this that expected value of y given xi is a function of xi? And now, because we are talking about linear regression analysis, therefore, we assume that the relationship between this expected value and xi is linear. For now, we are assuming this, right? So let's take an example here. Let's say we can say that our consumption expenditure is linearly related to our income. Fine. So how can we depict a linear relationship? It can be written as expected value of y given xi is equal to beta naught plus beta 1 xi. That is how we represent a linear function, right? Now, in this equation, this beta naught is our intercept term. And this beta 1 is known as the slope coefficient, right? And what do we mean by intercept? Intercept means that if my weekly income is 0, then what will be my conditional mean, which is very rare, but we have this value. And then we have the slope coefficient, which represents that as my xi changes by a single unit, right? Then what would be my change in this conditional expectation? That is what my slope coefficient represents here. And together, both of these are known as regression coefficients. Or we can also refer to them as parameters. So this is our deterministic PRF. Now, why do we have this term deterministic here? The reason behind that is, if we are for any given value of xi, right? If we are given the value of beta 1 and beta naught, we can easily compute the value of expected value of y given xi. For example, let's say that for xi, x1 is equal to 80 and I have my beta naught as, let's say, 1 and beta 2 as 2. Then I can easily plug in these values and I can find my conditional expectation where this x1 is equal to 80. So I can easily compute this, which will be equal to 1 plus 2 into xi. So that is why 2 into 80. So this will give me 161. So this has given me a deterministic value. Now let's move on to our second type of PRF function, which is non-deterministic random or stochastic population regression function. So to understand this, let's go back to our example. Let's go back to this table. So in this table, if we consider an individual family's weekly consumption expenditure, let's take it here. So that is 120, right? But the conditional mean that has been taken into account in the model is 125. So in the model, we are considering this, even though the individual family's consumption expenditure was 120. So how we take this difference into account? So for that, we have the concept of disturbance term, which is equal to have as deviation of individual yi from the expected value of y given xi. This ui is known as stochastic error term or stochastic disturbance term, right? We consider this to be random, right? This is random. It can take positive values. It can take negative values also, fine? Now, we can rewrite this equation as expected value. We can rewrite this equation as yi is equal to expected value of y given xi plus ui. Also, what does this ui account for? Ui also account for all those factors which influence the dependent variable but haven't been included in the model. So what does this mean? Let's understand this with the help of an example. Again, in law of demand, we are just taking, when we talk about inverse law of demand function, we have A minus B of QX, right? So in this case, we are only looking at impact of price on quantity demanded. But we know that quantity demanded is actually a function of many other factors, like it is also influenced by income, price of related goods, taste and preferences, and so on and so forth. But all of these factors are not included in the model. So all those factors which are neglected in the model are included in this UI, and this function, which is yi is equal to expected value of y given xi plus ui, is our non-deterministic or random stochastic PRF. Why it is stochastic? Because of our random error term. And this component is our deterministic component. And this is our non-deterministic component. And we know that expected value of y given xi, as we have seen above, that this is nothing but beta naught plus beta 1 xi. So we can write this as beta naught plus beta 1 xi plus ui. So this is all, or right? So this is our non-deterministic or random or stochastic PRF, right? Next concept that we have to understand is sample regression function. So why do we have a sample here? So the reason behind that is constructing a population regression function, constructing a model on the basis of PRF is very difficult and very tedious task. Why is that? So Let's take an example that I want to construct a model on how my weekly income, of how the weekly income is impacting the weekly consumption expenditure of an entire country. Now, going to every individual and collecting data from them is not possible, right? It is very tedious. And so what we do instead of that, we out of this entire population, we randomly select group of individuals, right? And we collect the data from those group of individuals, and on the basis of that data, we try to find out the approximate value of our entire population. So that is why we have sample regression function. For instance, in the example above, let's say we have drawn a random sample. So in this case, when the families which had a weekly income of 80, I have just selected randomly a single family, and that single family had a consumption expenditure of 70. Similarly, I have run with the families which had a weekly income of 140, I had randomly selected any one family and their weekly consumption expenditure was 95. So I have constructed two samples from this population, right? So that is an example of sample. So therefore, sample regression function can be referred to as the estimate of PRF on the basis of sample information. And here we need to remember that although this estimates the PRF, it does not estimate the PRF very accurately, right? So this estimation is not accurate always. Why is that? The reason behind that is sampling fluctuations. Now, different samples will actually give us different estimated values, right? So because of that, for instance, the conditional mean I am going to get from this sample will vary as compared to the conditional mean that I am going to get from sample number 2. So that is why, because of sampling fluctuations, it does not accurately estimate the PRF, but we try to get the best approximate of PRF, right? We try to get a sample regression function which is as close as possible to our true value of population regression function. Now, there are two types of sample regression function. Again, first is the deterministic SRF. For deterministic SRF, let's first remember what was a deterministic PRF. So that was y expected value of y given xi is equal to beta naught plus beta 1 xi, right? So SRF is nothing but estimate. So therefore, our deterministic SRF will be yi hat is equal to beta naught hat plus beta 1 hat xi. So why do we have a hat here? Because we are taking a sample, and in the sample they are estimating our population parameters, right? Population variables. So that is why. So here yi hat is my estimator of yi, expected value of y given xi. Beta naught hat is my estimator of population parameter beta naught, and beta 1 hat is my estimator of population parameter beta 1, right? So this is there. Next, we have the second type, which is the non-deterministic random or stochastic SRF. Again, what was a random PRF? That was given as yi is equal to beta naught plus beta 1 xi plus ui. So this can be written as yi. So our SRF in this case would be yi is equal to beta naught hat plus beta 1 hat xi plus ui hat, right? Again, beta naught hat, beta 1 hat are our estimators of population parameter, and this ui hat is known as my residual, and this is an estimate of my error term. Now, what is the difference between an estimate and an estimator? So let's see that we have these definitions, that an estimator, which is also known as a sample statistic, is a rule or formula or method that tells how to estimate the population parameter from the information provided by the sample. For example, this sample mean, which is taken as 1 upon n summation of xi, this estimates our population mean mu, right? But when we get a particular numerical value by the estimator in application, when I'll put on some numerical values in this formula, and the particular value that I will achieve, that is known as an estimate. So for example, in this case, let's take a sample of 5, 7, and 9. So therefore, on calculating my sample mean, that is 7. So this particular value is my estimate. And when we have not taken any particular numerical value, just the formula, that is my estimator. Right? So residual is actually the estimate of population error, and these are the estimators. Next, we have the concept of sample regression line. So the graphical representation of a deterministic SRF is known as sample regression line. So we had y naught hat, yi hat is equal to beta naught hat plus beta 1 hat xi. So if we plot this graphically like this, so if xi is 0, we will have it as, let's say, beta 1 hat. And if assuming that beta 1 hat is positive, so our SRL, our sample regression line, will be something like this. So for different samples, this sample regression line will vary. Fine. So now our objective is, therefore, from our discussion so far, our objective is to estimate the population regression function as yi is equal to beta naught plus beta 1 xi plus ui on the basis of sample regression function, which is given as yi is equal to beta naught hat plus beta 1 hat xi plus ui. Right? Now, remember that in this case, this is yi, and we know from the deterministic nature of sample regression function that this is nothing but yi hat plus ui hat. Therefore, we can define a residual as a difference between the actual value of yi and the estimated value of yi. Right? So let's plot this out. So let me take any one value, let's say xi, and corresponding to that, I have a population regression line taken as this, and I have a sample regression function taken as this. Right? So sample regression function will be giving me the value of yi hat, and let's say the actual value is somewhere here. So this is my actual value of yi, right? And so sample regression function will be giving me estimated value of expected value. So PRL will be giving me expected value of y given xi, right? So the difference, so this difference between actual value and the estimated value will give us the residual ui. And if we are talking about the difference between the actual value and the conditional mean, that will be giving us the error term. Fine. So this is the major difference between the two. And what we can conclude from this figure is that our yi hat has actually, this is an estimator of expected value of y given xi. Because this yi hat is lying above the expected value of y given xi, therefore it has overestimated. So yi hat has overestimated expected value of y given xi. So I hope this is clear. And at last, more often than not, our analysis is based upon single sample from some population. But because of sampling fluctuations, our estimate of PRF based on SRF is at best an approximate one. We have already discussed that. Now, so as we have seen that our SRF is an approximate of PRF. Right? So we want a method, we want an SRF such that it is as close as possible to PRF. So to get that objective, to achieve that objective, we have the method of ordinary least squares. So this method will construct a sample regression function which will be as close as possible to our population regression function. Fine. Let's discuss the method of ordinary least squares. So this was given by Carl Friedrich Gauss. Right? And this method, so under this method, because as we have already in our objective, we have seen that SRF isn't directly observable. Right? Why? First, because it takes into account the population. And another reason is that when we take our SRF, PRF, we have beta naught plus beta 1 xi plus ui, right? And these two coefficients, beta naught and beta 1, they are actually unknown but fixed parameters. So that is the reason our population regression function isn't directly observable, and we estimate, we take SRF to estimate this function. So what was our SRF here? This was taken as yi is equal to yi hat plus ui hat, right? So we had ui hat is equal to yi minus yi hat. And we want this sample regression function to be as close as possible to the true population regression function. So how can we achieve that? Because we know that our residual term is depicting the difference between actual and the estimated value. So what we can do is minimize the sum, their sum, right? But actually there is a limitation attached to minimizing just their sum. What is that limitation? Let's understand this with the help of a figure. Let's take our figure, and in this figure, we have plotted our sample regression function. Right? So this is our sample regression function. And let's say that at x1, my actual value was somewhere here, and my estimated value is y1 hat, which is given by sample regression function. So the difference between these two will be my residual term u1 hat. Then let's take x2. Again, let's say my actual value was somewhere here and my estimated value is y2 hat. So the difference between them will be residual u2 hat. Again, let's take x3. So let's take the actual value to be here and the estimated value to be here. So this is our residual in this case. Similarly for x4, where this is my actual and this is my estimated. So this is my u4. Now what's happening? So when we are taking sum of residuals, that would be equal to u1 plus u2 plus u3 plus u4. hats, right? So in this case, actually, every residual is getting equal importance. Every residual is getting equal weightage, even though from the figure we can see that U1 hat is much more widely scattered from SRF as compared to U2 hat or U4 hat. Still, they are getting equal importance. Still, this U2 hat is getting the same importance or weightage as U1 hat, even though it is more closer to our SRF function, right? So that is why we do not take the sum of just the residual terms. And also one of the consequences of taking the sum of the residual terms is that this can be positive, negative, any values. And in the long run, what can happen is that our positive and negative values can cancel each other out, or the sum can be very small, even though they are widely scattered. So to avoid those problems, we don't take sum of residuals. Instead, we take the sum of squared residuals, which gives more weightage to those residuals which are more widely scattered, right? So that is why we take sum of squared residual and we minimize the sum of squared residuals. Now, remember what our SRF was? Our SRF was given as yi is equal to beta naught hat plus beta 1 hat into xi plus ui hat, right? And the residual therefore can be written as yi minus beta naught hat minus beta 1 hat into xi. Now our objective is to minimize the sum of squared residuals, right? So we will be simply plugging in the value of a residual term here, which is equal to yi minus beta naught hat minus beta 1 hat xi whole square. Now we wish to minimize the sum of squared residual. So on the basis of first order condition, we will be differentiating the sum of squared residual with respect to the estimators present in this residual, which is one of them is beta naught hat, and equating this to 0, right? And now solving for it will give us summation twice of yi minus beta naught hat minus beta 1 hat into xi. And using the chain rule, because we are differentiating with respect to beta naught hat, this will give us minus 1 is equal to 0. Now taking 2 and minus 1 to the right hand side will leave us with yi minus beta naught hat minus beta 1 hat xi is equal to 0. Let's open this summation. So we will get summation of yi minus beta naught hat into summation of 1, because beta naught hat is a constant and the summation is over I or observation values. So beta 1 hat summation of xi is equal to 0. Now taking these terms on the right hand side, we will get summation of yi is equal to beta naught hat summation of 1 minus plus beta 1 hat into summation of xi. Now solving this, summation of yi is equal to beta naught hat into summation of 1. If we are assuming that the sample size has n number of observations, then summation of 1 will give us n plus beta 1 hat into summation of xi, right? Now we will be using some manipulation. Remember what is the mean of y? That is taken as yi upon n. So we will be taking this n on the right hand side and we will be substituting the value of the summation of yi, which is equal to n y bar is equal to beta naught hat into n plus beta 1 hat. Similarly, x bar is equal to summation of xi upon n. So we will be substituting value of summation xi, which is n into x bar. So dividing both sides of this equation with n, we will be left with y bar is equal to beta naught hat plus beta 1 hat into x bar. taking this beta 1 hat into x bar on the left hand side, we will be left with beta naught hat is equal to y bar minus beta 1 hat into x bar, and this is our OLS estimator of beta naught. So this is our OLS estimator of beta naught, right? Which is our interceptor. Now, we also need to calculate the value of beta 1 hat. So for that, we will be differentiating our sum of squared residuals with beta 1 hat and equating it to 0. So on that basis, again, using the chain rule and differentiation, we will be differentiating this. So we will be getting summation 2 of yi minus beta naught hat minus beta 1 hat xi. But now we are differentiating with respect to beta 1 hat. So that will give us minus of xi is equal to 0. Taking the 2 and minus 1 here on the right hand side will leave us with an equation that will be yi minus beta naught hat minus beta 1 hat xi into xi is equal to 0. Opening this equation will give us summation of yi into xi minus beta naught hat into summation of xi minus beta 1 hat into summation of xi square is equal to 0, right? Taking these two terms on the right hand side again, we will be left with summation of yi into xi is equal to beta naught hat into summation of xi plus beta 1 hat into summation of xi square. Now, in the next step, we will actually be substituting the value of beta naught hat, which was nothing but y bar minus beta 1 hat into x bar, right? Into summation of xi plus beta 1 hat into summation of xi square. So this will yield us, now opening this equation, so yi xi is equal to y bar, because this is a constant, summation of xi minus beta 1 hat into x bar into summation of xi plus beta 1 hat into summation of xi square. Now, we will be using yi xi. Let's take this equation on the left, this term on the left hand side, y bar summation of xi, and we will be taking beta 1 hat common on right hand side. We will be left with summation of xi square minus x bar into summation of xi. So this will give us beta 1 hat as summation of yi xi minus y bar into summation of xi upon summation of xi square minus x bar into summation of xi. Now again, we will open this up by substituting the value of y bar, which is equal to summation of yi upon n, right? So we will be writing this as xi minus summation of yi upon n into summation of xi upon summation of xi square minus summation of xi upon n into summation of xi square xi. Taking the LCM, we will be left with the value which is n into summation of yi into xi minus summation of yi summation of xi. The denominators will get cancelled out in numerator and denominator. So summation of xi square into n minus summation of xi whole square, right? So this is our value of beta 1 hat. Now, here, this is the value of beta 1 hat. But remember that the beta 1 hat can actually also be, if we manipulate this equation further, we can actually also write this beta 1 hat as summation of yi minus y bar into summation into xi minus x bar upon summation of xi minus x bar whole square, right? So how can we counter check this? So simply take the numerator in this case, open this up, and with further same manipulation that x bar is equal to summation of xi upon n, we can actually come to this numerator in this case. Similarly, for denominator, open this up and we will be coming back to this denominator, right? So this is another way of writing beta 1 that I will be discussing in this topic are the numerical properties of OLS estimators. So numerical properties are actually those properties which are holding after we have applied the OLS method, right? Regardless of how the data were generated. Fine. So some of the numerical properties of these OLS estimators beta naught hat and beta 1 hat are, first one is that they are point estimators. Point estimators means that every beta naught hat or beta 1 hat will give us a single value of population parameter, right? Second property that we have is that OLS estimators are expressed solely in terms of observables, that is x and y, therefore they can be easily computed. Now if we look at our OLS estimators, which was calculated as beta 1 hat, which is equal to summation of yi minus y bar, xi minus x bar. So basically this just depends on yi and y bar. It just depends on xi and value of x bar. And all of these are actually given to us or can be easily computed. So that is why beta 1 computing beta 1 hat is very easy. Similarly, if we see our beta naught hat, again it is given as y bar minus beta 1 hat into x bar. If we can compute beta 1 hat, then we can easily compute our beta naught hat as well. So that is why they are OLS estimators are easy to compute. Next, they are saying that once the OLS estimators are obtained from the sample data, this sample regression line can be easily obtained. So the regression line obtained has the following properties. So once our OLS estimates are formed, we can actually even easily obtain the sample regression line. What was our sample regression line? Our sample regression line was given as yi hat is equal to beta naught hat minus beta 1 hat into x, right? So now I have a given value of xi. I have computed beta naught hat and beta 1 hat. So I can easily compute my sample regression line. And how, so the first property that this sample regression line after it has been computed will follow is that it passes through the sample means of x and y. How can we show that? We have actually computed the value of beta naught hat as y bar minus beta 1 hat into x bar, right? So this shows that our sample regression line will actually pass through sample means, right? So we can also show this graphically. So for graphically, we can also show this graphically. So for graphical representation, let us draw sample regression line, right? And let's say, take a point here. So this is my sample regression line. At this point, I have the corresponding x bar on this x-axis, and on the y-axis corresponding to this point, I have a y bar, right? So this is the graphical representation of this equation basically. Value of the estimated y and mean value of estimated y equal to yi hat is equal to mean value of actual y. What do we have as yi hat? Yi hat is equal to beta naught hat plus beta 1 hat x. Simply substitute because we need the actual value. We need a comparison between actual and estimated value. So how can we introduce actual value? With the help of beta naught hat, which is equal to, so substitute at its value, which is y bar minus beta 1 hat x bar plus beta 1 hat into xi, right? Now, on opening this up, we will have yi hat is equal to y bar minus beta 1 hat x bar plus beta 1 hat xi, right? Let's take out this term as common. Let's take out beta 1 hat as common and we will be left with x bar minus of xi, right? And let's simplify this further. Yi hat is equal to y bar and I'm taking out the minus from that. So we will be getting beta 1 hat xi minus x bar. Now let's take the summation on both sides. So we will have summation of yi hat is equal to y bar because it is a constant into summation of 1 plus beta 1 hat into summation of xi minus x bar. Now this term is 0 because sum of deviation of mean of actual values from their mean is actually 0. So here we are taking a deviation of actual value from their mean, so it is 0. So we are left with summation of yi hat is equal to y bar into, if our sample size is n, so we will have an n. Now let's divide both sides by n, or let's take this n on the left hand side and we will be left with a sample mean. We will be left with the mean of estimated value and the mean of actual value of y. And this is what our property was, that the mean value of estimated y is equal to mean value of actual y. Third property is that the mean value of residuals is 0, which means that ui hat bar and okay. Remember that whenever we are taking a mean, because it is a constant, so we don't use this I in the subscripts, right? So we won't have these I's, right? So we have this ui hat, u hat bar is equal to 0. That is what this property is saying. How will we have this? Now go back to the first order conditions. So in this first order condition, we had this as our first order condition. So what did we get? This point here, this step. So in this step, actually, we are having, this is nothing but summation of ui hat and this is equal to 0. Now what is u hat bar? This is equal to ui hat upon n. Now because our numerator is 0, so this is 0 and that is what our property was talking about, right? Then moving back, this now, as a result of preceding property, the sample regression function yi is equal to beta 1 hat plus beta 2 hat xi plus ui can be expressed in an alternative form where both x and y are expressed as deviation from their mean values. So we can also basically express our sample regression function as a function which is deviating from there, where x and y are represented as deviation from their mean value. So how do we do that? So here's the proof. So we have yi is equal to beta naught hat plus beta 1 hat xi plus ui hat. This is our sample regression function. We also know that y bar is equal to beta naught hat plus beta 1 hat x bar because of value of beta naught hat that we calculated. Now let's subtract equation number 1 from equation number 2. So 1 minus 2 will give me yi minus y bar is equal to, now beta naught hat and beta naught hat will get cancelled out. Beta 1 hat is a common value. We will be left with xi minus x bar plus ui hat. So this deviation from mean. So we are having a deviation of mean of an y, and this is deviation of x from their mean. So we can express it as small yi is equal to beta 1 hat into xi plus ui, where small xi is equal to xi minus x bar and small yi is yi minus y bar. That is their respective deviation from means. Now remember that this is our SRF when we have a stochastic form. Right? And an SRF in case of non-stochastic form. can actually be written as yi hat is equal to beta 1 hat xi, right? So let's so remember this because it's useful for our next property, which says that the residuals ui hat are uncorrelated with predicted y. So how do we prove this? We simply take summation of ui hat with yi, and we need to prove yi hat, and we need to prove that this is equal to 0. So for doing this, we will simply, for proving this, we will simply first substitute the value of yi hat, which was equal to this. So that would be beta 1 hat xi. So this can be written as beta 1 hat into summation of ui hat into xi, right? Now this can be written as beta 1 hat into summation of what is the value of ui hat? That is yi minus beta 1 hat into xi using this equation into xi. Let's open this up. We will get beta 1 hat into summation of yi xi minus beta 1 hat square into summation of xi square. Now, another very important thing that we will be using here is that our beta 1 hat is actually equal to summation of xi yi upon summation of xi square. Remember, when we had done this property, when we have calculated the value of beta 1, I have told you that it can be written as deviation from their mean. So this can actually be written as small yi, small xi upon summation of xi square is equal to beta 1 hat. So that's what we are using down there, right? So that is why we have this. Fine. So if taking this on left hand side, so we will be left with beta 1 hat into summation of xi square minus beta 1 hat square into summation of xi square. Now multiplying this, and it will be same as this term. Both of them will cancel out and we will get a 0. What we needed to prove. So therefore, our residual and our predicted value of yi are uncorrelated to each other. Then we also have the property that our residuals are uncorrelated to our explanatory variables, which means that summation of ui hat into xi is equal to 0. This is what we have to prove. How do we prove this? Very simple. Go back to our first order conditions. In those first order conditions, here in this step, so this is nothing but my ui hat. And this is my xi. They are 0. Therefore, they are uncorrelated to each other, right? So that was our property number 5. Last thing under this model are some of the assumptions underlying OLS method, which is the classical linear regression assumptions, or they are also known as the statistical properties of OLS estimators. These assumptions, these properties are actually dependent on how the data was generated. Basically, these properties are related. Now, we know that our yi is a function of xi as well as our error term, right? So actually, the statistical properties are related to how the data was generated, means it is related to the properties of our xi's and our error terms, right? So the first property that we have is a linear regression model, which means that our population regression function is linear in parameters. So for that, we had our yi is equal to beta naught plus beta 1 xi plus ui, right? Plus ui, right? So linear in parameter means that our parameters beta naught and beta 1 have to be linear. We can't have a beta 1 square. Then the function would be quadratic in parameters, right? So we don't have a function. So we have a function which is linear in parameters, but we can actually have a function which is non-linear in explanatory variables. This means that our explanatory variable xi, this can be non-linear, this can be log of x, this can be x squared, this can be anything, this can be quadratic, non-linear, anything. But our parameters need to be linear, right? Then we have fixed x values in our population, as we have discussed in the hypothetical example. And if the values of x are taken stochastically, right? If we are taking the value of x randomly along with the value of dependent variable, then we need to ensure that these x values are actually independent of these error terms. Fine. This means that basically there should be no relationship between the explanatory variable and our error term. This implies basically that the covariance of xi and ui should be equal to 0. And whenever we have covariance as 0, the correlation between these two is also 0. So why is that? Because the formula of correlation between xi ui is actually equal to covariance of xi ui upon standard deviation of xi and standard deviation of ui. If our numerator is 0, therefore our correlation is also 0, right? Third assumption is 0 mean value of disturbance term. This means that the expected value of ui given xi is equal to 0. So this is the case of stochastic regressor, when our regressor is stochastic, or we can say expected value of ui is equal to 0 when we are talking about a non-stochastic regressor, right? So what is this implication of this assumption? Actually, this means that all those factors which are not included in the factor in the model, they won't be affecting the mean value of y. Fine. So this implies basically that if we have positive ui's, if we have negative ui's, all of those positive and negative ui's will cancel each other out such that their average value will be 0. Then next implication of this assumption is that there is no specification error. Now, when do we have a specification error? We have a specification error if we take a wrong functional form. Wrong functional form means basically that, let's say my model had to be, this was my correct model, beta 1, beta naught plus beta 1 x. But I have included a model which is equal to beta naught plus beta 1 log of xy. So basically I have included a wrong model. So that is basically wrong function. I have included a wrong functional form in my model. So that will lead to a specification error. Another reason why we have a specification error is when we exclude some very relevant variables from the model, or if we include some irrelevant variables in the model, that also leads to specification error. So due to this property, we won't have any specification errors in our model. Then the third property is that the variance of ui is constant. This is also known as homoscedasticity. Homo means same and skedasticity means variance, spread. So this basically means equal variance. So we are saying that variance of ui, which can be written as expected value of ui minus expected value of ui given xi whole square. This is a formula of variance. is equal to, we know that this value is 0 because there is no correlation between these two. So expected value of them will be 0. So we will be left with expected value of ui square given xi. So this variance is constant. So how do we show? Actually, what do this imply? This implies that in our example, we have seen that as our weekly income was increasing, our weekly consumption, average weekly consumption expenditure was also increasing. But this property says that with the increase in our weekly income, with the increase in our X values, our variance will remain constant. So if we had this as a function, so this spread around this X1, so this spread will be same like this, right? So the spread, no matter what the value of X is, will remain the same around their conditional mean. So that is what this assumption of homoscedasticity means, right? Fine. So this was the assumption of homoscedasticity. Then we have no autocorrelation between disturbance term. For this, let's say for any given two xi and xj from two different samples where I is not equal to j, then there won't be any correlation between the error terms of these two samples. This means that the covariance between ui, uj will be given xi, xj will be equal to 0, right? Now, what do this mean? This basically implies economically, what is its implication? The implication is that there is no systematic pattern followed by error terms. Which means that let's say for in the first sample, I got U1 to be a positive. In the second sample, I got U2 to be negative value. In the third sample, I got U3 again to be positive, then U4 again negative. So there is a systematic pattern that is being followed. So when we have autocorrelation, no autocorrelation assumption, then this systematic pattern won't be followed by the error terms. This is what this implies, assumption implies. Then lastly, we have number of observations. They should also be always be greater than number of parameters to be estimated, because this is a actually this is a concept of linear equations in which whenever we have to estimate number of unknown parameters. For instance, if we have to estimate two unknown parameters, which are beta naught and beta 1, then the number of observation, number of equations that we always need are at least 2 or more than 2. Only then it is possible to estimate them. Otherwise, it won't be possible to estimate them. We will get no solution in that case. Lastly, nature of X variable. In nature of X variable, first thing is that we should have no outliers. Outliers refer to the values which are very large from the observed observations that we have. For example, let's say that we have taken a fixed income to be 260. And then we have taken next fixed income to be 1000. So that value, when observation is very large than the actual data, that is known as an outlier. So we won't have any outliers, we assume that, because outliers can actually influence our results. So to avoid that problem, we'll have no outliers. And the second point that we have in nature of X variable is that same values of X in a sample is not possible. Reason behind that is when we take summation of X upon N, we have taken the mean, right? So if all of these values are equal, we will get Nxi upon N. Both of them will get cancelled out. We will have Xi. So basically our Xi is equal to X bar. Now go back to what our estimator beta 1 hat was. That was summation of yi minus y bar into xi minus x bar upon summation of xi minus x bar. Now, if both of them are equal, this will be denominator would be 0, and we won't be able to calculate our estimator. So that is why in a sample, same values of x is not possible. So that was the concept of linear regression model and OLS estimation. Thank you so much.